Hi, my name is Dima Rekesh. I am a distinguished engineer with IBM's Internet of Things Analytics team. This brief video introduces the software-defined radio (SDR) proof-of-concept application that we developed for the Project Mountain platform. Now, as you probably already know, Project Mountain aims to create a revolutionary, massively scalable Internet of Things platform where large numbers of IoT devices can easily communicate, exchange data, run analytics, and execute transactions in real time. Software vendors can develop software for the devices and enter into smart contracts of arbitrary complexity with one another. To accomplish that, Mountain uses the Ethereum blockchain technology. You package your applications as simple Docker containers. You just need to make sure that the code is compiled for the type of device that you are targeting, such as Raspberry Pis, which are part of our pilot. Now, we have encouraged our pilot participants to optionally attach a small software-defined radio dongle to their Raspberry Pis. This Raspberry Pi, shown here, retails for just about $22 in Amazon, but yet it can capture radio signals in the range between 24 and 1750 megahertz, which is quite powerful. Now, back to the SDR application homepage, you can see here the devices that are participating in the pilot mapped by their geographic location. Now, when the device joins the pilot for the first time, it spends a couple of hours capturing the radio frequency scan of the entire spectrum that the device sees. And so this page over here, towards the bottom, shows the aggregated information for all of the devices that are shown on this page. The slider down below here allows the users to very easily explore the frequency spectrum that they see and look for any interesting features. Now, when they want to interact with a particular device, all they need to do is basically click the balloon that corresponds to this device, and then they proceed to the device homepage. So this is the page where you can explore the radio spectrum directly associated with a particular device. The lateral resolution is controlled by the minimum and maximum frequencies, in this case 107 and 1.8 megahertz. In order to capture a waterfall, all you need to do is to click this button here that says click start waterfall. And the lateral resolution is controlled by the number of frequency bins. And the vertical resolution is a multiplication of the samples per second times the runtime per second. So I'm going to start one waterfall right now, and hopefully it'll complete within the next couple of seconds. I'm also able to control the color scheme of the waterfall by controlling these sliders over here. This is the amplitude of the signal as translated to the color over here. Now, in this particular case, we're looking at a FM range. And so what we did, in order to make things a little bit more fun, we implemented a feature which enables us to actually capture a radio clip associated with a particular frequency. So hopefully in the next couple of seconds, we'll see a nice strong signal at this frequency over here that corresponds to 107.29 megahertz. And there's a little slider here that enables you to select any frequency you want. So as you can see here, by changing locations of these sliders, you can move the spectrum that you're exploring. You can actually see the spectrum visually here on this page, and it enables you to very quickly zero in on an interesting feature here. So let me try to play this sample here. As you can see here, we were able to successfully capture this sample. There's another feature. There's a system called the RDS, also known as the Radio Data System Protocol. So many radio stations actually broadcast a digital signal along with their data. And so if you wanted to see the textual information associated with a particular station, all you do is to click this button, and you will see the data coming in the lower part of this page. Really quickly, one other feature that is part of the application. On the home page, you'll see a little airplane icon. If we click it, we end up on this airplanes page. Now, this really is an example of how a network of devices equipped with software-defined radios could be used to map and track airplanes that are flying overhead. So, in the background, when our participating devices are not busy running requests and jobs, they listen to and analyze the 1090 megahertz automatic dependent surveillance broadcast, also known as simply ADS-B signals, that commercial airlines use to broadcast their locations, as well as to track each other. So this data coming off the participating Raspberry Pis is aggregated into the cloud and displayed on this map. You can see that I can see airplanes within pretty decent range of about 100 miles from the location of that particular Raspberry Pi that we saw in Northern California. So the interesting thing is, and you can click on any airplane to see the trajectory of it as the device was tracking it. So commercial systems such as FlightAware use a very similar approach to create a comprehensive map of flights around the world. So in summary, the SDR application highlights one of the most important things about the Mountain platform, that it enables multiple jobs from different software vendors to be running on a device in parallel. And so in this case, tracking airplanes does not require to have a dedicated device or dedicated software. Well, thank you very much for watching, and we hope that you will sign up for the pilot of the Mountain platform. Just navigate to tremor.hovitos.engineering to get started. Thanks again.